All right. So let me try and share my screen. I hope you can see the screen. Yeah?
Yes, I can see.
Okay. Now, as I say, if we don't understand what we are working with, then it is very difficult to get hold of an axiomatic system. So we will be working with a notion of sets as we know. Sets, what do you mean by a set? Can you tell me? Yeah? Julia?
Yes, I can.
Yeah? What is a set? Okay, Julia?
Which I don't know how to put it.
Okay, what are you thinking?
Okay, I think is that I think that is where we categorize. Is where we categorize in certain numbers. Maybe when we put them in the braces. I think so.
Okay, Julia? Hello?
Hi, sorry. I think that just from my knowledge, a set is just sort of, I don't know if I want to use the word group yet, but it's sort of like a set of objects. You can have a set of numbers that are selected on for some arbitrary reason. So you can have the set of even numbers, that's a set. You can have one as a set. You can have an empty set. So it's a group or a sort of collection that are objects, they're things, and then you can apply functions to them. That's my understanding.
Yeah, yes, it is in this sense that we will first start off. So we will consider the term set to mean a bag or a collection. Collection of objects, and with only one stipulation. The stipulation is that given an object we would know now this is very crucial, we would know how, I am not specifying, but we will know whether it is contained in that bag or not, whether it is inside the bag or not. And so that will be a loose way of looking into sets, and with this let us see how much can we develop. And we will see that with this much of mathematics usable things can be developed. And then finally I will introduce a strange paradox which will seemingly say that all that what we have done is nonsense. And then the only rescue from that would be to properly axiomatize. Axioms are nothing else but properties. So giving certain properties which we would not question any further. And once we give those properties, we will see that it is almost impossible to construct any such paradox And all that we have done so far would very nicely fit into it. Okay? So this is our program. Now, so we will take a set like this, and if we have an object A and a set A which contains this object, we will write something like this. We often say this is the belongs to symbol. And if it doesn't, we would write something like this. Okay? So you just cross it.
Yes.
So now the set is just a collection. So for instance, you would have seen Venn diagrams. So it doesn't matter whether we say that this set consisting of 3 beads, whether we draw it like this or we draw it like this, it doesn't matter. Okay? So that means
Yes.
there is no reference to the shape. The shape doesn't matter. If we are interested in 3 beads, it doesn't matter whether the 3 beads are in a glass of water or are on a table or wherever. The set of 3 beads only says that it has those 3 beads. Okay? So it is. So in other words, as Julia said, there will be some strange. So how do we? And that is actually this key of this key behind this word no. So sets are just another name for a common property. For a common property which belongs to its elements. Right? So a set is just another name to that. So we are just collecting objects which satisfy this property. Now again, this word property is very, very loosely used. Well, in our examples, we will have very concrete properties, but when we come to axiomatization, we will see what does this property actually mean. Okay? And, people, since Julia is working in coding, you will obviously know that this property is a very, very restrictive term. And we are going to have such restrictions. But we need to first make our hands a little bit dirty. So for instance, if we say it is the set of all numbers, so then our property A is, say, numbers, whole numbers. And then the set of all numbers, we would agree to write like this, either in this form. In fact, why did I write? Either in this form, or we would also write it in this form. So this is a symbolic way to say this is the set of all those x, all objects x, such that the property A is true. So now you see, if we fix our notion on this property, so we have some way to understand this meaning of the word no, because we will search whether an object has this property or it does not have this property. Well, if it doesn't have this property, then it doesn't belong to that set. Okay? There is another issue. So, in other words, we will consider a set to be another way of giving a name or another way of naming a property which is common to all its elements. So that is how we will look at sets. Okay? As simple as this. Now let's see what sets can we start from this. As I said, the first set is, we already looked into this. We can have set of all numbers less than or equal to less than some number n, some whole number n. So this will be, usually this is denoted by Zn. So for instance, we will also have all real numbers. It is denoted by R and so on. You should have seen lots of such sets by now. But then here is another property. Very weird. So, what is this? Can you say?
Oh, I think it's X such that X not equal to X.
Yes, what will...
X such that.
Yes, correct. But what is... Can you think of any object which satisfies this property? For all that we know about the notion of equality, can you think of any object X which can satisfy this property?
No,
Yeah?
no. It's like if you put 2 there, you can't say 2 doesn't equal 2, like so.
So if you take any object X, it has to be equal to X, right?
Yes, yes.
So no object satisfies this property. But this is well, if X is equal to X is a property, then X is not equal to X is also a property. Negation of a property is expected to be a property, right? If the property doesn't hold. So this is a property. And from all that we have said so far, this should actually give us a set, and it is what is known as the empty set. And we denote it like this. It is not phi, this is called the empty set. So the empty set is precisely the set of all X such that X is not equal to X. Okay? So, you see, from nowhere we started off with one set at least. Okay, something else? Say, the property is X is equal to an object A. So that means okay?
Yes.
So this set is usually denoted in this form. So it is a set which has exactly one element, which is A. Okay? In particular, we have this set. The set which has only one element, which is the empty set. Okay? We will see later on why I am calling this boldface 1. But here is another one. Or X is equal to B. So for this, Okay? So this is nothing else but the set which has exactly two elements. X is equal to A or X is equal to B. Okay? So two elements. So in particular, since we have already got hold of two sets, so we have this set. Or if we use this symbol, and we call this boldface 2. Okay? So similarly, if we go on like this, we have boldface 3. And so on. So you see, just this simple step actually is giving us so many sets already. Okay?
Yes.
Okay. Now there is another notion that needs to be introduced. It is how do we think of two sets are equal? How do you decide on this? When will you say that two sets are equal? Yeah?
Actually, I don't have an idea. You can answer.
Julia?
Two sets are equal when all of the elements within them are the same in each. And they share the same property.
Correct. That's the most natural way to think about it. Because we have taken sets exactly to be a naming of a property. It's another name of a certain property. So if we have two sets, that means they must be giving us the same property and so on. But there is one little snag over here. The little snag is, since the word property is also not quite well understood, let us keep the things that are not that well understood below the carpet, okay? So let us try and think in terms of elements only. So we define a particular relation. So we say that given two sets A and B, A is a subset of B, or we also say that B is a superset of A, and we write this like this. What does this mean? This means this formula. So this property, X belongs to A, implies X belongs to B. Well, I wrote it in this form. You can, for the time being, think of this as if X is an element of A. I'm just writing it in words. Then X is an element of B. Okay? So this expanded thing I have written in short like this. And you have possibly seen this, but here are some nice properties A is always a subset of A. By the way, I have written down some notes and I'll put them up tonight. There will be proofs. So while I'm in these lectures, I'll roughly take 40 minutes to say something, but the notes that I will put up will have, apart from the major theorems or crucial ones, the rest will be proved for you. So the major ones will be proved. The simpler ones will be given a hint. So your understanding would be very nicely reflected if you try and work out those proofs during this week. And next time when we meet in the discussion session, you come up with what is your problem with them. Okay? So, these are the properties. This is okay, and here is a third one, which I will, although this one also I have proved in the notes, but this is a crucial one. I'll come back to this proof, but before I do so, at this stage, remember, this is saying if X is a member of A, then X is a member of B. So as Julia said, A and B must have the same member. So the best way would be to say A is a subset of B and B is a subset of A. And that's exactly the definition. Remember, equality of sets is now being defined. It is not as given. Okay, so it's a defined object. So two sets A and B are equal, and we write this if A is a subset of B and B is a subset of A. And this exactly means, as we can see, that means whenever I take X as a member of A, it is a member of B, and the second one says it's, and every member of A, B is a member of A, so A and B have the same elements. We cannot have anything different. Coming back to this equality, therefore, there is a nice thing over here. This is same as right? Because this set, B is a member of this and so is a member of this. A is a member of this and so is a member of this, and this, therefore these two sets are equal. So this one follows from the definition of equality. Okay? But this tells us one moral. It tells us there is no point in permuting, in arranging the order in which you list down the elements of a set. Remember, the first time I said a set just says that what elements it contains, nothing more. In particular, it doesn't matter how you write down its elements, in what order. It doesn't matter. You can write it down in any order as you wish. But still, if you write down the same elements, the sets are same. So that's the first thing. Another thing to note, that this is equal to AA. Again from the definition of equality. So it doesn't make any sense to repeat the elements of a set. The only thing is whether an object is an element or it is not an element. It doesn't add if you say it is an element 10 times. Okay? So no repetition. Alright? No repetition, no respect to order or whatever. Okay? In which you list things. But still, the sets turn out to be the same. So that's another issue. I'll come to this proof and then I'll stop for today. So the proof of So remember, I have to prove if X is an element of the set called the empty set, then X must be a member of A. Now observe, this is quite strange. If X is a member of this, the way we have defined this is X such that X is not equal to X. Now, how on earth can we take an element which is not equal to itself and show it as a member? Now, this brings us to, this is one of the, in many cases we will be tackling such statements. See, it looks like, so this part is one block and this part is another block. So X belongs to this is one statement. X belongs to A is another statement. And let me shorten this to this symbol. It's easier to write. You should very quickly adopt yourself to, instead of if then writing it in this way, getting to this symbolic manipulation. However, now this is one statement, this is another statement, this is a third statement. Statements like this are often called implication statements. An implication statement has three parts. The first part, which is on the left hand side of this is called the implication symbol. So on the left hand side of the implication, that is called the hypothesis. So see, the hypothesis is if what you assume, right? That is your hypothesis. And this one is often called the consequent. Consequent means, you have heard the word consequently, means what follows. So hypothesis is something which you start off arguing with. Consequent is what you get from there. Now, this implication process is a that is the whole, when we formalize things we will see, but this is possibly the first time I'm doing, it's a deep thing. What we are going to use is known as classical Boolean logic. What logic tells us is how do we assign truth values to statements. So a statement in Boolean means there are only two truth values. Either it is true or false. Just as a side issue, let me tell you that there are several other logics. There are logics in which there are three truth values. We don't no more say it to be true or false. There are logics where there are many other truth values. Okay? And people study them. But we will be looking in something called a Boolean logic, where there is only two truth values. We will be seeing this again, but this is the first time. So this is a serious step. In classical Boolean logic, the implication statement, so it looks like something like this, where alpha is the hypothesis, it's a statement, beta is the consequent, and the implication statement is this. So let us try and tabulate the truth values. So alpha can be true and beta can be true. Alpha can be true, beta can be false. So these are the only four truth values which are possible. Now this is something important. In classical Boolean logic, we say that the implication statement can only be false in this case, when the hypothesis is true and the consequent is false. Let us not try and ratiocinate why it is like this or why is it so. It is just a stipulation. This is how the Boolean logic works. Why am I not going to expand on this, give several reasons, is the moment you change your stance, you change your type of logic, this one will change. This implication will have other assignment of truths. And this is actually one of the places of contention. So let me not say, expand on why. I'm not going to say it. I say, in classical Boolean logic, this is the stipulation. And in all other cases, it is true. So firstly, the implication statement is true always except when the hypothesis is true and the consequent is false. So this is the only case when it is false. Now let's look into these two. These two tell me that if the hypothesis is false, whatever be the consequent, true or false, it doesn't matter. I need not look into it. The implication statement is true. So if the hypothesis is false, I don't look into the truth value of the consequent. The implication is true. So this kind of a deduction is often called a vacuous implication, because vacuous comes from the word vacuum. Hypothesis is false. You have nothing to check. Yet you are telling me the implication is true. This is strange about classical Boolean logic, and this is the bone of contention for other logics to take birth. This is the oldest form of logic that was started by Aristotle, why Aristotle even before, and people started questioning this, and that's how other forms of logic came up. But let's not go into that. In our mathematics that we are going to do, we will adopt this classical Boolean logic. Okay? Let there be no other question about this. So now let's come back to this. So we are going to ascertain the truth of this implication statement. But this one is false. No x can belong to the empty set. So it is false. So therefore, the whole implication statement is true. And hence this means okay, is it clear? Mavuta, are you still there?
Yes, I'm still there. I'm following. Then I understood the classical language. Then I'm following where you are right now.
Julia?
Yeah, makes sense.
Okay, two more people came in. We'll get introduced. One tells its initial is CZ. So you are CZ, and the other tells me is S. So I hope you are following. So now I'll stop here. I will put up these notes. I hope you can see my screen. I was writing something like this. So it is just, your textbook is something which you have, but this is kind of trying to explain it. But the textbook, remember, it goes the other way around. We have just changed the order. We'll be doing all of it. So I have just told you all of this that I have written, and there are something more that we have done. I have written down. So I'll send you up to this page. This up to this fourth section. So that means the first 11 pages. Okay? All right? And
yes.
there are some equations like this which I am sure you have seen already, used already, but try to give a proof. And then we will see next time how, if you get stuck, how we do about it, how we go about it, and then from next time we'll proceed further. Okay?
Yes,
Okay.
yes.
Yeah? Someone trying to say something else? Hello?
It's all right.
Okay.
Hello.
Hello, yes?
No, we are following whatever you're saying.
Okay. Okay. So, as I said, next time I will put up these notes just now, so you will get them. So I'll put up. So you have no problems in downloading PDF files from my UNISA, right?
No, I don't.
Okay. So I'll put up these notes in my UNISA, as well as this recorded part. Okay? So you can go through if this recorded part helps, I don't know.
All right.
Then you can, next time when we meet, the first 15 minutes will be given to you to ask questions, your problems, and so on and so forth. And then in the last 40 minutes, I'll give the next part of the lecture, okay? So let's see. I hope in this way we will create a lot of mathematics, and then in the end we will see the axioms, and then we will understand the real goal and the impact of the axioms, and how does it help to make a paradox-free presentation of the whole system. Okay?
Yes, yes.
All right. So with that, I stop now.
Okay. Thank you very much.
Thanks.
Thank you.
Thank you very much.
Thank you.
Yes, yes.
By the way, CZ, who